Okay, so welcome to our second lecture in discrete mathematical structures. In the first lecture, we didn't really talk about much other than the syllabus, who I am, and what is to be expected throughout the semester. In this lecture, we're going to talk about discrete mathematics as a subject. So I'm assuming that most of you really don't have an idea of what discrete mathematics means, right? And I want to convey in this lecture what it is, so you can describe it to your fellow majors, people that ask you, things like that, right? Now, there should be some type of flag to you, by the way, that like 70%, 80% of the students in this class are CS majors, computer science majors, right? So why are you guys in here? Why do all of you have to take computer science? And for the data science majors in here, you probably are curious about this as well. So to answer the question of what discrete mathematics is and why you're in this course, I need to review a few things. And again, I apologize for having a broken leg. I'm going to be hobbling around by the board. So this is lecture 2. And this is all about what is discrete mathematics. And if you have your mic on, please mute it unless you're going to say anything. I'm picking up a lot of sound right now. Okay, so what is discrete mathematics? Well, to answer this question, as I just mentioned, keep on repeating myself, we have to recall a few ideas. And these ideas start with the number systems that all of you might be or are for sure familiar with. So I'm going to recall a few things. First, we need to remember what the natural numbers are, or the counting numbers. So natural numbers typically denoted by this fancy looking N are the numbers, and this is set notation that I'm using, which we'll get to in a few weeks. 1, 2, 3, 4, dot, 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 off to infinity. Okay. These are sometimes called the counting numbers because these are the numbers we use to count. And this set of numbers is probably one of the oldest sets of numbers that humans have ever used, right? Like if you imagine that you're living a long time ago and you want to keep track of seasons, you're going to count the seasons that are happening, you're going to count the days possibly, you're going to count the number of crops that you have. So it's the obvious set of numbers to use for counting purposes, right? Now, much later, after the advent of this number system, another number system appeared, which I will say, I'll call the wholes. So the whole numbers. Okay. And I will use a fancy W like this. And this is the set of all numbers 0, 1, 2, 3, 4, dot, 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 off to infinity. Okay. Now this is a very similar number system to the naturals, or the counting numbers, right? With one exception, that thing, the number 0. So imagine, again, that you're living like a long time ago when you're worried about like eating and just like providing for a family or whatever, like just barely making it by. yes, you would want to count things, but where is the need for zero? When would you ever have that need to point at something and say there's zero of those things, right? It's not so clear how soon that should happen, right? In human history, like how soon the notion of zero would occur. So it actually took a long time to get from the natural numbers to the whole numbers. That zero is an abstraction. Like so much of mathematics, abstraction is where, I don't know, the power of mathematics really shows itself. Okay, that sounded cheesy, but hopefully you get what I'm saying. Okay, so the naturals, the whole numbers, and then the next number system is the integers. Probably my favorite set of numbers. In this set is denoted by this fancy looking Z. And this consists of the positive and negative whole numbers. Okay, so what would be like a motivating factor for this set of numbers to appear? Well, imagine that you're in a civilization and you start trading for product between this object and this object, whatever, right? You might encounter a case where you owe someone some object or currency, right? So if you owe someone something, then you're negative that value. So that might be a motivating factor, but I'm not going to go into that. I'll just provide a link in the description in this video below and on Blackboard for a little bit about the history of the number systems. I think it's fascinating. Okay, so currently naturals, whole numbers, integers, these are nice numbers, nice, like easy to grasp numbers. The next number system is where we start to get a little bit more abstract. And this number system is called the rational number system, or the rationals. Now, bear with me for a moment. I'm going to use notation that you haven't seen before. But it's almost necessary for me to use this notation to describe this set of numbers. So this set of numbers is denoted by a fancy Q, and this is equal to the set of all A over B such that A and B are integers and B is not equal to 0. Okay, so I'm going to walk you through this set builder notation here. So this is read again, all A over B. So these are ratios. Okay, all A over B. This colon symbol here is read such that A and B are elements of the integers, meaning they're integers. So this right here just says A and B are integers. And then the rest you can read, right? So, okay, these are ratios of integers, okay? Okay, so I have a quick question right now. Okay, so now that I've answered that question, back to the rationals. what are some examples of rationals? Well, anytime you can write a ratio with a non-zero denominator of integers, you have a rational number. So some examples of rationals would be like 1/10, right? That's an integer, and the denominator is non-zero. Another example would be 4, right? 4 is a rational number because 4 is equal to 4/1, right? So because I can write 4 as a ratio of integers, it must belong to this set. Now, in fact, anything in this set of integers must belong in the rationals, because I can just take whatever integer I'm looking at, divide it by 1, and then I have a ratio that satisfies this condition to be in this set. It's rational. And since every whole number is an integer and every natural number is an integer as well, all of these numbers are contained in this set. So maybe I should just make a point of that. The rationals contain all elements from the naturals, the wholes, and the integers. This set is somehow, it seems like it's like the biggest set out of all of these because it contains all of them. And as we'll learn later on in the semester, all of these sets, the naturals, the wholes, and the integers, are subsets of the rationals. Any element in this set is in there, any element in that set is also in there, so forth and so on. Okay? Now, you would think, at least I would think, after being told about these sets of numbers, that that's everything, right? Like, what number could possibly exist that's not in this thing, right? Like, another example of a rational would be like 1.5. That's a rational, right? Or like 0.25, right? 0.25 is a rational because it's equal to 1/4. In all sorts of decimal expansions, we can express as a ratio of integers, which means they have to be in there. So what else could there be, right? Like, I would have no idea how to find something that did not live in there in this set, right? So this was the case for a very long time, until around the time of the ancient Greeks, where a new number was discovered. Consider the following: a triangle. Suppose you have a right-angled triangle with sides of unit length 1 and 1. Now, you should recall from simple geometry, that is a horrible right-angled triangle. There. That this squared plus that squared is equal to that squared, right? So the famous formula, a squared plus b squared is equal to c squared, right? This Pythagorean theorem. So if that has length 1 and that has length 1, what is the length of the hypotenuse of that triangle? Well, so we have 1 squared, which is 1, plus 1 squared, which is 1. So this is going to be 2. 2 is equal to c squared. C must be equal to the square root of 2. This right here has to have length square root 2. This is a problem. And as the story goes, and I don't know if this is true, but this is what everyone always says, this fact that that hypotenuse has length square root of 2 was discovered by a member of this ancient cult called the Pythagoreans. They worshipped ratios. They thought that everything in the world could be expressed as a ratio of integers, and that's the way that the world was. It was almost like their religion, that everything was a beautiful ratio. And this poor guy that brought to the Pythagoreans the attention, this fact was, I think, murdered, because this number, square root of 2, turns out to not live in the set of rational numbers. It cannot be written as a ratio of integers. And because of this fact, it kind of broke their worldview. The guy was obviously into Satan or whatever, and they had to get rid of it. But how did they know that it wasn't in there? How did the Pythagoreans figure out that this number, square root of 2, it appears so simply, it even comes from the Pythagorean theorem. How did they know that that number did not belong in that set? Well, I'm going to show you how. They knew that it did not belong in this set by proving that it did not belong in that set. So I'm going to show you this proof. Okay. So over here, just recall, rational numbers is the set of all ratios of integers with non-zero denominator. Okay, so that's really the only fact we need to start with. Actually, there's one more. A number, so this is fact 1, next fact would be n is even if n is equal to 2 times some number k, where k is an integer. Okay, so this is another fact. Even numbers, by definition, are twice an integer. Okay, so we have definition of even, definition of being the rational set of numbers. Now, with that information, in some clever argumentation, we can show that that number does not belong to that set. And I'm going to write this as a theorem. And most people attribute this theorem to Euclid, though it's unsure if Euclid was the person that wrote this theorem. And mathematicians tend to believe that this is the most beautiful of all arguments with respect to proofs. And in discrete mathematics, we're going to learn how to prove arguments very similar to this. It might seem daunting at first, but I'm going to walk you through it as the semester goes on how to write arguments in a formal way. So the theorem states that the square root of 2 is not rational. So notice that I've been using the epsilon symbol to denote something is in a set. Now I have the epsilon symbol with a little cross going through it to denote that it's not in that set. So that's the claim. Okay. Now again, bear with me. It's going to seem daunting, but we'll get there in the coming weeks. Proof. So by way of contradiction, so contradiction means we're going to assume the opposite of the statement. Okay, so the statement says the square root of 2 is not in there. by contradiction, we're going to assume that it is, and then find ourselves in something that's false. We're going to show the opposite is false, which means the original statement is true, which is one of the properties of propositions that we'll cover next lecture. So, by way of contradiction, suppose square root of 2 is indeed a rational number. Okay? Now, as soon as we suppose anything, we can typically reference something like a definition. So, if square root of 2 is indeed rational, that means that by definition, it has to be, you can write it as a ratio of integers with non-zero denominator. So, I'm just going to say that. Then, by definition, square root of 2 equals some numbers a over b, where a and b are integers and b is not equal to 0. Okay. All I did was make a claim that it is in there, and then I looked at what it means to be in there, and then I stated it. That's it. Okay. So we can write square root of 2 as a ratio of integers. But so now imagine that you have something like 4 over 12, right? That's a ratio of integers, but you can reduce it to what? So 4 over 12 becomes 1 over 3, right? So anytime you have a ratio of integers, you can reduce it. So we have a ratio of integers. Let's just assume that we've already reduced it so that a and b share no common factors. Okay. So maybe I'll say like, moreover, we may suppose a and b share no common factors. Since otherwise we could just like reduce it and get rid of those common factors. Okay, so very important points, just to really emphasize it. A and B share no common factors. Okay. Okay. Next, observe that square root of 2 equals to a over b implies that 2 is equal to a squared over b squared, right? If I square both sides of this equation right here, I get 2 on the left-hand side, and then on the right-hand side, I get a squared over b squared. Simple algebra, that's all I've done. Okay? So with this equation here, I get maybe hence a squared is equal to 2 times b squared. I just multiply both sides of this equation by b squared. Okay? And I isolate a squared. Now, here is something that takes a small leap of like thought. So first observe a squared is equal to 2 times b squared. B is an integer, so b squared is an integer, right? So a squared is equal to 2 times an integer, which means that it satisfies the definition of being even. So I can just write that out so you, to be clear. So hence a squared is equal to 2 times b squared. Implying a squared is even. Okay, so we agree that a squared is even. Now here's the slight jump, and we'll actually prove this maybe next week or the week after. If a number squared is even, then the original number must also be even. Now think about that. Definition of being even means that you're twice an integer, right? You have a factor of 2. So if the square has a factor of 2, it must be the case that the original number had a factor of 2. Since otherwise, where did that factor of 2 come from? So hopefully you're with me on that. So we have that a squared is even, which means that a must be even. Since where did the factor of 2 come from? If you're multiplying a number by times itself, that's the square, and neither one have a 2, there's no way that the product will have a 2. So the original number must have a factor of 2. So hence a squared is equal to 2 times b squared. So a squared is even. Implying a squared is even. And I'll just put a comma there, and a must be even. Okay. So a must be even. All right, so I'm continuing the argument over here. So we've established 2 facts right now. A and B share no common factors because we just kind of reduced this ratio. And we've established that if this is the case, that we can write square root of 2 this way, then the number a must be even. Okay. Next, observe that, so looking at this equation here, a squared is equal to 2 times b squared, that b squared is equal to 2, or no, I'm sorry, b squared is equal to a squared divided by 2, right? I just divide both sides of this equation by 2. Okay, so we have a formula for b squared. Let's see if we can discover anything about its properties. Well, I know by this fact right here that a is even, which means if it's even, it's 2 times some integer. I don't know what that integer is. I just know that a squared is equal to 2 times b squared, but the number a itself, I have no idea what that number k is, and I honestly don't care. I just know that a is equal to 2 times something. So I'm going to write that out. So since a is even, a is equal to 2 times k for some integer k. Because we established that a must be even, we know that it's 2 times something. Okay? Now, I'm going to take that value for a, and I'm going to plug it into that formula. So maybe I'll continue by saying hence b squared, which is equal to a squared over 2, must be equal to 2 times k all squared over 2, because that's what a is. So this is what? 4 k squared over 2. 4 divided by 2, 2 k squared. I know something now. So b squared is even, right? B squared is equal to twice an integer, which means it satisfies the definition of being even. But if b squared is even, like we reasoned before, if b squared is even, then b must be even. We've established another fact. By following the logic and taking step by step, we've established the third thing. Now, looking at what I have circled here in green, all of those things together. So let's think about, let's just recap first. We assumed the opposite of this statement, which means that square root of 2 is a rational number. Then by definition, I can write it as a ratio. I write it as a ratio, and if I need to simplify it, I can. I just assume that I've simplified it all the way down, which means that a and b share no common factors. Okay. Moreover, if I can write square root of 2 as that formula, then I can solve for a squared, and I see that a squared is equal to 2 times b squared, which implies that a must be even, or 2. Using that same formula that I got by assuming the opposite of this, of the original statement, I further observe that b squared is even, which implies that b is even. There's a problem. The problem is all 3 of these propositions, logical propositions, right? Propositions are statements that are either true or false, right? Declarative statements that are either true or false. All 3 of these things cannot happen at the same time. How can it be possible that a and b share no common factors, but they're both even? If they're both even, they have a factor of 2. That means that there's a contradiction. A contradiction is a logical statement that is false. So if we assume the opposite of this statement here and follow through deductive reasoning and use of definitions and a little bit of algebra, we get an entire statement, a statement together that is false. I'll just write it out. This is a contradiction since a and b share no common factors. And that is the end of the proof. Why is it the end of the proof? Well, looking up here to the original statement, propositions, logical propositions, are either true or false, right? And if a proposition is true, then the opposite of it must be false, okay? If the opposite of a proposition is true, then the original is false. There's this dichotomy, it's a binary relationship between a proposition and its negation, as we'll learn next lecture. So the negation of this statement, which is what we suppose at the beginning of our argument, the negation is false because these things can't happen at the same time, which means that the original statement, that thing, must be true. This is a theorem and we've proven it. It's true forever and always, that number right there can never be written as a ratio of integers, because if you try, you get a fallacy, you get a contradiction, which means the original statement that it's not in the set of rationals has to be true. This is a technique in proofs called proof by contradiction. You show that the opposite of the statement is false, which means the original statement must be true. So this is, I wasn't able to write it the way I wanted to because I have limited board space, but this is really the first example to most mathematicians of a proof in the modern sense of the word proof. A clear logical argument using an interesting technique such as proof by contradiction. So what have we just established? We've established that there are numbers that do not belong in that set, such as that one. So we've established that there are what are called irrational numbers. Square root of 2 being one of them. And unfortunate for the Pythagorean cult, this is not the only one. In fact, there are more irrational numbers than there are rational numbers. They're both infinite sets, but one has more than the other in terms of the elements of the set, which is a strange thing to think about, and something that we're going to talk about later in the semester. We're going to talk about how some sets of infinite number of elements can be larger than other sets. It turns out the number of irrational numbers is far greater than the number of rational numbers. Even though prior to this argument, we were kind of thinking maybe that was all the numbers, it's definitely not the case. Now, what does this have to do with discrete math? Well, honestly, just showing you the proof and giving you an example of a proof is a part of discrete math, because in discrete math, we're going to learn how to logically prove in a rigorous way arguments. That's part one. We're using number systems like the rationals, part two. We're sequencing together steps. That's like algorithm building in a sense. In fact, proving statements, if you're good at proving, you will be good at designing your own algorithms. Important for all of you. Okay? But really, to get back to the beginning of the lecture, when I said we wanted to answer this question, what is discrete mathematics? The distinction is this. It's about the sets of items that we study. So, discrete math studies finite sets and the rationals. So that's set Q. That is the study of discrete mathematics. It's a study of operations, properties on finite sets, collections of objects, unordered collections of objects, and the rationals or any subset of the rational numbers, like the natural numbers, or in particular, the integers. most of the mathematics courses that you've taken in the past have focused on what's called continuous mathematics. So when you take a course like college algebra or trig or pre-cal, you're most definitely dealing with continuous mathematics, which more or less you can think of the study of the reals, which is typically denoted by the fancy R, and is roughly equal to, well, not roughly, it is equal to the rationals together with the irrationals. Now, this might not seem like that much of a difference, rationals versus the rationals with the irrationals, but it's a huge difference. And it has to do with that fact I stated earlier, that there are way more rationals than there are irrational numbers. And by that, I mean that in continuous mathematics, when you're looking at the real numbers, so the rationals together with the irrationals, you're dealing with what's called a dense real number line. I'll say that, just to not get into the details of it. But basically what it means is that if you have a real number line, there are no holes on that number line consisting of all the reals. So no gaps, I'll say, on the real number line. Whereas if you looked at a discrete set, such as the rationals, and you tried to put them in a continuous line, there's holes pretty much everywhere. Everywhere. In between any two rational numbers that you pick, there'll be an irrational number that's separating them. Whereas on the real number line, you pick any two numbers on the real number line, there's another real that's like squished in between them. There's no holes at all. So here, with a discrete set such as the rationals or any other discrete set, and again, when I say discrete set, I mean a finite or subset of the rationals. There are gaps everywhere. Everywhere. There's little holes everywhere. And it's a completely different type of mindset to think about this versus that. You can think of the real number line as a continuum without any holes in it. You should think of discrete sets as packets of information. So if you're a subset of the rational numbers, you're somehow split up into a bunch of little packets of information, of numbers or whatever. Whereas on the real number line, things are smooth and there's no holes. That's why in a course like college algebra or pre-cal, you have a real number line crossed with a real number line called the Cartesian plane. That's why you have these smooth looking curves. Whereas for something that's discrete, like the rationals or any other discrete set, if you tried to plot something, it would look like this. There'd be holes everywhere. So that's the distinction. Now, this is important. This is a very important distinction for several reasons. Most notably, for those of you that have taken calculus, that derivatives of functions in continuous mathematics require a continuum. They require an infinite limiting process. If there is no continuum, you cannot take a limit. which means that derivatives don't exist in the realm of discrete mathematics. Measuring the rate of change of a discrete function is not the same as measuring the rate of change as a function on the continuum. The techniques required are completely separate. Okay, so that's a very important distinction. But because we're running out of time, I should probably mention why so many computer science majors have to take this course, and why the data science majors are in here. Well, I guess maybe historically speaking, discrete mathematics started in computer science programs. It was a course taught by computer science professors. But there was kind of it's kind of a fuzzy area back then because the original computer scientists were mathematicians. So it's kind of fuzzy on that notion. However, going back to what I wrote as underneath this discrete math thing here, notice it says finite sets and the rationals or any subset of the rationals, right? But finite is the really important part. So the real numbers, infinite, dense, uncountably infinite, it's just everywhere. So using techniques on the set of real numbers with the continuum, those techniques will not work on finite sets of objects. So a set is just a collection of elements with no repetition in it. That's the definition of a set, naive set theory. So what's a really obvious object that all of you in this course deal with in your major? So as computer science majors and data science majors. What's a really obvious discrete object? Well, computers, right? A computer is a finite set of instructions, a finite amount of RAM, memory, storage. It is a finite collection of things, which means that a computer is a discrete mathematical object, right? What is an algorithm? An algorithm is nothing more than a discrete or a finite collection of instructions. That's a discrete mathematical object, right? This is an important aspect of how computer science started. Computer science started from discrete mathematicians, right? And I think that's the most important thing to remember as you're taking this class, that you're in here because the tools that you use, or the machine that you use, i.e. a computer, is one of these objects. And the techniques used to work with these objects are the techniques that will be found in discrete mathematics. So pretty much everything as a CS major or data science major is discrete mathematics. Even things like databases, relational databases are these things called graphs. That's a discrete object, right? And we'll get into graph theory later in this semester. And it's one of my favorite subjects because, well, I just love it. And my PhD is in graph theory. I've studied discrete math for a very long time. One more note before we end. That square root of 2 thing that we found, that irrational number, we can't write it as a ratio, which means that it has an infinite decimal expansion with no repetition. We can't ever write out the decimal expansion of square root 2. It goes on to infinity with no repetition, just like pi, for example. Most of you are probably familiar with that notion. So what does that mean for someone programming? Well, think about how square root of 2 or pi must be stored in computer memory. We can't store the full actual number. We have to store a truncated, finite approximation to it. That can be dangerous. For example, if you're working for a company and you're launching some billionaire into space, and you have these algorithms that are working on physical laws, like implementing these physical laws, and the algorithms a lot of times pi will show up in these physical law equation things, right? So you're programming, you're writing your algorithm. Every time that pi in the equation appears on your, like in your code and is being looped over, each time you're looping over it, you're only using an approximate value to the true value that was derived in mathematics, which means that if you loop that pi in that equation a million times, you're incurring a little bit of error in your projections a million times, which means that little bit of error can start blowing up, and then you could shoot a billionaire into the sun. These types of concerns are real. It's a part of a study of a field called numerical analysis. But understanding that there is a difference between finite mathematics and continuous mathematics is vital to being good at what you do as computer scientists and data scientists. Okay, so hopefully this kind of illuminated a little bit about discrete mathematics. And in the next lecture, we're going to dive right into the beginning with logic and understanding the formalisms behind logic so that you can also prove statements like the statement that I proved earlier with the square root of 2. So that'll be it for our recording.